It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
Over the past 18 episodes, we've built a foundational understanding of this transformative technology, from classical search and logic, through the statistical revolution of machine learning, and deep into the neural networks that power today's most advanced systems. For most of our journey, the AI we've discussed has been a ghost in the machine, an intelligence living in the digital realm of servers and data centers. It processes text, analyzes images, and generates code, but it has no hands to touch the world, no feet to walk through it. It is, in a word, disembodied. But what you're hearing now, that is something different. That is the sound of AI leaving the digital ether and entering our world. It's the sound of intelligence being given a body. Today, in episode 19, we explore what is arguably the most ambitious, challenging, and consequential frontier in all of artificial intelligence: robotics and embodied AI. We'll ask the fundamental questions. What happens when an AI can physically interact with the world? Why is this leap from processing information to performing physical action so monumental? We will define embodied AI as the integration of artificial intelligence into physical systems, like robots, autonomous vehicles, or even entire factories, enabling them to perceive, reason, and act within real-world environments. This is the paradigm shift from informational AI to physical AI. Our roadmap for today is clear. We'll begin with the profound why, exploring a radical idea from cognitive science called the embodiment hypothesis, which argues that true intelligence requires a body. Then we'll deconstruct the how, the core engineering loop of sense, plan, and act that forms the backbone of every intelligent robot. We'll investigate how these systems learn, moving beyond rigid programming to adapt through trial and error using reinforcement learning. Finally, we'll take a tour of the what, surveying the most advanced embodied agents operating today, from specialized warehouse bots to the new wave of humanoid robots and the autonomous cars navigating our city streets. And for those of you who have been with us throughout this curriculum, you'll see that this episode is not just another topic. It is a grand synthesis. The computer vision models we studied are the robot's eyes. The natural language processing systems are its ears and part of its brain. The reinforcement learning algorithms are its method of learning and adapting. Embodied AI is the domain where all the abstract concepts we've learned become concrete, integrated, and interdependent, working together to create the most sophisticated AI systems in existence. This is where the ghost finally meets the machine. To begin our journey, I want you to consider a classic philosophical thought experiment. The brain in a vat. Imagine a brilliant scientist's brain is removed from their body and kept alive in a jar, connected to a supercomputer that simulates a perfectly realistic world. The brain receives all the same nerve impulses it would in a real body. It can think, reason, and experience this simulated reality. The question is this brain truly intelligent in the same way a person is? For centuries, the dominant Western view of intelligence, heavily influenced by philosophers like René Descartes, would say yes, this is the Cartesian model of a disembodied mind. The idea that cognition is a purely mental, non-physical phenomenon, separate from the messy business of the body. Our intelligence, in this view, is the software, and the body is just the hardware it happens to run on. For a long time, this was the guiding philosophy of artificial intelligence as well. Early AI, what we now call good old-fashioned AI, or GOF-AI, focused on symbolic manipulation and logical reasoning, treating intelligence as an abstract problem-solving process, completely divorced from physical reality. But in the latter half of the 20th century, a powerful counterargument emerged from the fields of philosophy, psychology, and cognitive science. It's called the embodiment hypothesis, and it makes a radical claim. Cognition is not just influenced by the body, but is deeply and fundamentally dependent on the experiences that come from having a body with sensory and motor capabilities. Intelligence, this theory posits, is not something that happens in the brain alone. It emerges from the dynamic, continuous loop of an agent perceiving its environment, acting within it, and learning from the feedback of that interaction. To understand why this is so crucial for AI, we need to talk about something called the symbol grounding problem. Imagine a traditional disembodied AI like a large language model. It might process the word heavy thousands of times in its training data. It learns that heavy is statistically associated with words like rock, lift, effort, and difficult. It can use the word heavy perfectly in a sentence, but does it understand what heavy means? The embodiment hypothesis says no, it's just manipulating an abstract, ungrounded symbol. Now, consider an embodied AI, a robotic arm tasked with sorting objects. It tries to lift a small wooden block, and its motors use a certain amount of current. Then it tries to lift a large metal weight. The motors strain, the force torque sensors register immense pressure, and perhaps the arm fails to lift it at all. Through this physical, sensorimotor experience, the robot grounds the symbol heavy in real-world feedback. It's no longer just a statistical pattern. It's a tangible concept linked to motor effort and sensory data. This is the difference between knowing the dictionary definition of a word and having a lived experience of what it represents. This idea was famously championed in the AI community by roboticist Rodney Brooks in his seminal 1991 paper, Intelligence Without Representation. Brooks argued against the prevailing GOFAI approach of building complex internal world models and logical reasoners. He proposed that intelligent behavior could emerge from much simpler, direct interactions between a robot and its environment, a bottom-up approach that was revolutionary at the time. This brings us to a critical point about the AI systems that dominate today's headlines. Large language models. The well-known problem of hallucination, where an LLM generates plausible-sounding but completely false information, can be seen as a direct consequence of their disembodied nature. An LLM is a master of statistical patterns and symbolic manipulation. It can tell you that an astronaut on the moon needs an oxygen tank because it has seen that pattern countless times. But if you ask it a novel question where statistical patterns lead to a plausible but physically impossible answer, it has no way to check itself. It has no body, no sensors, no experience of physics or causality to ground its statements in reality. Its knowledge is ungrounded. Therefore, the drive to create embodied AI isn't just about building useful robots to do physical tasks. For many researchers, it's about solving a fundamental limitation of current AI. By giving an AI a body, we force it to confront the physical world, to ground its internal models in real-world consequences. This is a proposed path to move AI from mere pattern matching to something that more closely resembles genuine understanding. If the embodiment hypothesis gives us the philosophical why, then the sense-plan-act loop gives us the engineering how. This architecture, sometimes called the perceive-decide-act cycle, is the fundamental operational blueprint for virtually every intelligent robot, from a simple vacuum cleaner to a sophisticated humanoid. It is the practical implementation of that dynamic coupling between perception, cognition, and interaction we just discussed. Let's break down each component of this robotic trinity. First, the robot must sense its environment. This is far more than just seeing. modern robots are equipped with a rich suite of sensors that provide a multimodal, 360-degree awareness of the world. Visual data comes from high-resolution cameras, often multiple, providing a stereoscopic view for depth perception. But light can be deceiving, so many robots also use lidar, which stands for light detection and ranging. Lidar systems send out pulses of laser light and measure how long they take to bounce back, creating a precise 3D point cloud of the surrounding environment, day or night. Autonomous vehicles like those from Waymo also use radar, which can see through rain and fog and measure the velocity of other objects. Internally, an inertial measurement unit, or IMU, acts like the robot's inner ear, using accelerometers and gyroscopes to track its orientation and acceleration, which is critical for maintaining balance. And for manipulation, force torque sensors in the joints and grippers give the robot a sense of touch, allowing it to feel how hard it's pushing or how much an object weighs. But this raw sensor data, a stream of pixels, laser points, and force readings, is meaningless on its own. It must be interpreted. This is the job of the perception stack, which is where the computer vision models we've discussed in previous episodes come into play. These neural networks process the raw data to build a high-fidelity semantic understanding of the world. They perform object detection to identify cars, pedestrians, and traffic lights, semantic segmentation to label every pixel in an image as road, sidewalk, or building, and 3D reconstruction to create a detailed geometric map of the scene. The output of the sense stage is not just data, it's a coherent, actionable model of the world. Once the robot has a model of the world, it must plan its next move. This is the cognitive core of the loop, the robot's brain, and it's the stage that has been most dramatically transformed by the recent AI revolution. In the past, robotic planning was often rigid and logic-based. An engineer would pre-program a set of rules. If obstacle is detected at distance X, then turn left. This works for simple tasks in predictable environments, but it's brittle and cannot handle novelty. Today's approach is far more sophisticated and often hierarchical. At the highest level, we now see the integration of multimodal large models, or MLLMs. These are models, similar to GPT-4, that can understand information from multiple modalities, like text and images. A user can give a high-level command in natural language, like, "Please get me the apple from the counter." The MLLM uses its vast common sense knowledge to decompose this complex task into a logical sequence of smaller steps. 1. Navigate to the kitchen counter. 2. Visually identify the apple. 3. Plan a grasping motion for the apple. 4. Pick up the apple. 5. Bring the apple to the user. This brings a new level of semantic reasoning and flexibility to robotics. But how does the robot decide on the specific physical motions? This is where a concept called a world model comes in. A world model is essentially an internal simulation of physics and the environment. Before executing an action in the real world, the robot can use its world model to imagine the future outcomes of several possible actions. For example, it could simulate a dozen different ways to grasp the apple and predict which one is most likely to succeed based on the apple's shape and position. This allows the robot to choose the optimal plan by preempting risky or inefficient behaviors without dangerous and costly trial and error in the physical world. This planning stage is where the true intelligence of the robot lies, and it is the area advancing most rapidly. While sensors and motors have improved steadily for decades, the recent breakthroughs in foundation models are supercharging the cognitive capabilities of robots. The bottleneck in robotics is increasingly shifting from mechanics to cognition. This means that a breakthrough in generative AI can now translate into a massive leap in robotic capability almost overnight. a phenomenon unheard of in the slow, iterative history of industrial automation. Finally, with a plan in hand, the robot must act. This is where the digital plan meets physical reality. The primary hardware components for action are actuators. The motors, hydraulics, or other devices that convert energy into motion, serving as the robot's muscles. These actuators drive the robot's joints, wheels, and end effectors, which are the tools at the end of a robotic arm, like a gripper, a suction cup, or a welding torch. However, translating a plan like move hand to coordinates X, Y, Z into reality is an immense engineering challenge in itself. This is the domain of control theory. A sophisticated robot like Boston Dynamics Atlas has dozens of joints, and moving just one arm requires calculating and sending precise, coordinated electrical signals to many different motors simultaneously, all while adjusting in real time to maintain balance and stability. To manage this complexity, engineers use advanced algorithms like Model Predictive Control, or MPC. MPC works by constantly predicting a few seconds into the future. At every moment, it calculates the optimal sequence of motor commands that will best achieve the desired trajectory over the next short time horizon. It executes the first command in that sequence, then immediately replans based on new sensor data. This constant cycle of predicting and replanning allows the robot to move smoothly and dynamically, adapting on the fly to disturbances like a slip of the foot or an unexpected push. The sense-plan-act loop is a continuous, high-frequency cycle. A self-driving car might run through this entire loop dozens of times per second. It is a constant conversation between the robot's brain and the world, mediated by its body. For most of their history, industrial robots have been incredibly powerful and precise, but also incredibly rigid. Think of the giant robotic arms you see in a car factory. They perform the same welding or painting task millions of times with sub-millimeter accuracy, but they are pre-programmed. A team of engineers has painstakingly coded every single movement. If the car model changes or a part is misaligned, the robot cannot adapt. It will continue to execute its rigid script, often with destructive results. This process of reprogramming is time-consuming, expensive, and requires specialized expertise. These robots are powerful tools, but they do not learn. The goal of modern robotics is to move beyond this brittle automation towards true adaptation. And the key paradigm for achieving this is reinforcement learning, or RL, a topic we introduced in episode 11. Let's revisit the core idea. In reinforcement learning, an AI agent learns through trial and error, much like a person or an animal. The agent exists in an environment and can take certain actions. After each action, it receives feedback from the environment in the form of a reward or a penalty. The agent's goal is to learn a policy, which is just a fancy word for a strategy, that maximizes its total cumulative reward over time. For a robot learning to walk, a positive reward might be given for moving forward without falling, while a large negative reward is given for falling over. The robot doesn't know how to walk. It simply tries random motor commands. At first, it flails and falls constantly. But over millions of trials, it begins to associate certain sequences of actions with positive rewards and others with negative ones. Gradually, it builds a policy that allows it to walk, then run, then navigate obstacles, all without a human ever explicitly programming the mechanics of walking. The catch is that reinforcement learning is incredibly data-hungry. It requires millions or even billions of trials to learn a complex skill. Having a physical, multi-million-dollar humanoid robot learn to walk by falling over 1,000,000 times is impractical, dangerous, and prohibitively expensive. This is why the vast majority of RL training for robotics happens in simulation. Engineers create highly realistic virtual environments, or digital twins, that model the robot's physics and its surroundings. In this virtual world, they can run thousands of instances of the robot in parallel, 24/7, allowing it to accumulate centuries of experience in a matter of days. They can safely test hazardous scenarios, like how the robot should react to being pushed over, without risking damage to expensive hardware. This simulation-first approach is central to modern robotics development. However, this leads us to one of the single biggest, most persistent challenges in the entire field: the sim-to-real gap. The problem is that no simulation is perfect. The real world is infinitely complex. There are subtle variations in friction on different surfaces, the way light reflects off objects, the slight delay in a motor's response, the noise in a sensor's readings, all of which are impossible to model with perfect fidelity. The result is that a policy trained exclusively in a pristine, idealized simulation can fail spectacularly when transferred to a physical robot. A robot that could walk perfectly in the simulator might immediately lose its balance and fall on a real floor. This discrepancy between simulated performance and real-world performance is the sim-to-real gap. Bridging this gap is a major area of research. One popular technique is called domain randomization. The idea is to make the simulation less perfect on purpose. Engineers intentionally introduce random variations into the simulation's physics and visuals, changing the friction, the lighting, the colors of objects, and the robot's own physical parameters. The goal is to train a policy that is so robust to this simulated chaos that the real world just looks like another one of these variations. Other approaches involve pre-training a model in simulation and then fine-tuning it with a smaller amount of data collected from the real robot, blending the scalability of simulation with the accuracy of real-world experience. Interestingly, the very existence of the sim-to-real gap serves as a powerful piece of evidence for the embodiment hypothesis we discussed earlier. It is the engineering proof that there is no perfect substitute for genuine interaction with the messy, unpredictable physical world. The dream of learning everything in a clean simulation before graduating to reality remains just that, a dream. The most successful approaches today use a simandrial strategy, recognizing that while simulation is an indispensable tool for accelerating learning, the final, crucial lessons must be learned through a real body interacting with the real world. We've covered the philosophy, the architecture, and the learning methods. Now, let's ground these concepts in the real world by taking a tour of the most significant embodied AI systems operating today. We'll see that a key debate is playing out in the industry, an idea perfectly captured by a classic sci-fi analogy. Is the future C3PO or R2D2? Is the goal to build a universal, human-like robot, or a diverse ecosystem of specialized machines where form perfectly follows function? Let's start with the specialists. The best example of this design philosophy is the Stretch robot from Boston Dynamics. Stretch is not designed to be a general-purpose helper. It has one job: unloading boxes from trucks and shipping containers, a monotonous and physically demanding task that leads to high rates of injury in warehouses. Its form is a masterclass in purpose-built design. It has a small, omnidirectional mobile base the size of a standard pallet, allowing it to navigate tight spaces in a warehouse without requiring any new infrastructure. Instead of two arms, it has a single, long, powerful robotic arm with 7 degrees of freedom, topped with a massive vacuum gripper that can pick up boxes weighing up to 50 pounds, about 23 kilograms. What makes Stretch an embodied AI and not just a pre-programmed machine, is its ability to adapt. It uses a swiveling perception mast, equipped with cameras and 3D depth sensors, to build a real-time map of the boxes inside the container. A custom machine learning algorithm processes this data to decide which box to pick next, even if the boxes are jumbled, damaged, or have shifted during transit. It makes all its decisions in real time, with no pre-programming required for each new truckload. Stretch is a clear example of decoupling intelligence from a human-like form. It doesn't look like a person because it's not trying to do a person's job. It's doing a specific task, and its body is optimized for that task alone. In stark contrast to the specialists, we are now in the midst of a massive investment boom in general-purpose humanoid robots. The core argument is simple and compelling. We have built our world, our factories, homes, and offices for the human body. A robot with a human form factor or morphology should theoretically be able to navigate our stairs, open our doors, and use our tools without requiring us to redesign our entire environment. Let's look at the leading contenders. First, there's Digit from Agility Robotics. Standing 5 feet 9 inches tall, Digit is designed primarily for logistics and warehouse tasks. Like moving totes and containers, its most distinctive feature is its backward-bending, bird-like legs, which provide exceptional balance and efficiency for walking and maneuvering. Agility Robotics takes a simulation-first approach, using NVIDIA's Isaac Sim platform to train Digit's whole-body control policies through billions of reinforcement learning trials before deploying them to the physical robot. Next is Phoenix from Sanctuary AI. Sanctuary's mission is explicitly to create the world's first human-like intelligence in general-purpose robots. Their focus is heavily on the AI control system, which they call Carbon. Carbon is designed to mimic subsystems of the human brain, integrating both symbolic and neural reasoning. A key hardware focus for them is dexterity, and Phoenix is equipped with some of the most advanced multi-fingered robotic hands in the industry, capable of delicate manipulation. Then we have Figure AI, which recently unveiled its Figure 03 humanoid. Figure's goal is to create a truly general-purpose robot for both commercial work and, eventually, the home. Their strategy is built around a tight vertical integration of hardware and software. The Figure 03 robot was designed from the ground up to serve their proprietary AI system, Helix, which is a vision language action model that enables end-to-end learning, taking raw pixels from its cameras and translating them directly into motor commands. And of course, there is Atlas from Boston Dynamics. For over a decade, the hydraulic Atlas was the undisputed research benchmark for dynamic locomotion. Famous for its parkour, backflips, and dancing, it demonstrated mastery of complex control algorithms, like model predictive control, to achieve its incredible stability. Recently, Boston Dynamics retired the hydraulic version and unveiled an all-electric Atlas, which is stronger, quieter, and has a much larger range of motion. This new platform is shifting its focus from pure locomotion to manipulation, using techniques like large behavior models to learn complex tasks from human demonstration via teleoperation. To help keep these players straight, let's summarize them in a table. First, Agility Robotics Digit. Its key design feature is its efficient backward-bending legs. Its AI system is focused on whole-body control, learned via reinforcement learning in simulation, and its primary target market is logistics and warehouses. Second, Sanctuary AI's Phoenix. Its key design feature is its highly dexterous, human-like hands. Its AI control system is called Carbon, which is modeled on human brain subsystems. Its target market is general-purpose labor across multiple industries. Third, Figure AI's Figure 03. Its key design feature is its tight vertical integration of hardware and software. Its AI system is Helix, a vision language action model for end-to-end learning. Its target market is general-purpose labor with a long-term vision for the home. Finally, Boston Dynamics Atlas. Its key design feature is its unparalleled dynamic mobility and strength. Its AI system is evolving from model predictive control to include reinforcement learning and large behavior models. And its target market is primarily R&D, pushing the boundaries of what's possible. This intense competition raises a fascinating strategic question. The specialized approach of a robot like Stretch is lower risk, with a clear and immediate return on investment in a structured environment. The humanoid approach is a much higher risk, higher reward bet on creating a foundational platform for all physical labor, a potential AGI with legs. We are watching a live experiment unfold, testing whether the future of robotics will be won by perfecting a single, useful form or by building a truly general intelligence that can be poured into any body. Finally, we must discuss what is arguably the most complex, widely deployed, and safety-critical embodied AI system in the world, the autonomous vehicle. On one end of the spectrum, you have the Waymo driver. Waymo takes a methodical, multi-sensor approach. Their vehicles are equipped with a full suite of lidar, high-resolution cameras and radar, which they fuse together to create a redundant and robust perception of the world. Their process follows a classic explicit SensePlan Act pipeline. First, they meticulously pre-map an area in high definition. Then their perception system identifies and tracks objects. A prediction module then forecasts the likely behavior of those objects. Finally, a planner calculates the safest trajectory for the vehicle. It is a robust, safety-first engineering approach. On the other end, you have Tesla's full self-driving, supervised system. Tesla has famously taken a vision-only approach, removing radar and lidar and relying solely on cameras. Their strategy is to build a unified end-to-end neural network. Instead of separate modules for perception, prediction, and planning, they aim to feed raw video from all 8 cameras into a massive network that outputs steering, acceleration, and braking commands directly. This approach relies on training these networks on an immense amount of driving data collected from their fleet of millions of vehicles on the road, effectively using their customers as a distributed data collection fleet. These two different philosophies, Waymo's explicit multi-sensor system versus Tesla's end-to-end, vision-only approach, represent one of the most significant debates in the field of embodied AI today. The videos are impressive. The progress is undeniable. But as we look to the future, it's crucial to separate the science fiction from the engineering reality. The path forward for embodied AI is paved with immense challenges, and it's important to start by debunking some of the most common public misconceptions. First is the myth that AI robots think and feel like humans. Despite their sometimes human-like appearance or behavior, these machines do not have consciousness, emotions, or subjective experiences. They are running incredibly complex algorithms on vast amounts of data to produce an output. A robot that says, "I am happy," is not feeling joy. It is executing a subroutine that has identified "I am happy" as the statistically appropriate response in that context. Second is the myth that humanoid robots are synonymous with AI. AI is and will remain primarily software. Most AI applications, from your spam filter to medical diagnosis systems, are disembodied. The humanoid form is a specific engineering choice for a specific set of tasks, not a prerequisite for intelligence. And third is the persistent fear that robots will take all our jobs. History shows that automation technologies tend to transform labor markets, not eliminate them. Robots are poised to take over tasks that are dull, dirty, and dangerous, freeing up human workers for roles that require more creativity, critical thinking, and social intelligence. New jobs will be created in programming, maintaining, and managing these complex robotic systems. With those myths addressed, let's turn to the very real, very difficult grand challenges that the field must overcome. The first is hardware. Battery technology is a major bottleneck. Most advanced humanoids can only operate for 2 to 4 hours on a single charge, far less than a standard industrial work shift, and heavy lifting drains them even faster. Actuators, the robot's muscles, still lack the combination of strength, speed, and subtlety of biological muscle, and creating truly dexterous, sensitive hands capable of tasks like peeling a banana remains a moonshot-level challenge. The second is software and data. The physical world is, as one researcher put it, unimaginably complex and unpredictable. The foundation models, trained on the relatively clean, structured data of the Internet, struggle when faced with the chaotic reality of physical interaction. They need billions of examples of physical interaction, from videos, simulations, or real-world trials, to achieve the same level of competence, and that data is far harder to acquire. The third challenge is economics and scaling. General-purpose robots are still incredibly expensive, with manufacturing costs ranging from $30,000 to $150,000 per unit. They are often built from bespoke, low-volume parts, with fragile supply chains. There are no widely accepted standards for components or software, making integration with existing factory systems difficult and costly. We are still a long way from a plug-and-play robot that can be deployed as easily as a new computer. So, where does this leave us? Throughout this episode, we've seen how giving AI a body forces it to confront the real world. This brings us to a final, crucial point. The pursuit of embodied AI creates a powerful, self-correcting feedback loop that is entirely absent in the world of disembodied, digital AI. Consider this. When a large language model hallucinates and gives you an incorrect fact, the consequences are often minimal. You might be misinformed, but the system itself experiences no negative feedback. It doesn't know it made a mistake. But when an embodied AI hallucinates, when it misjudges the weight of a box, the friction of the floor, or the location of a wall, the failure is immediate, unambiguous, and catastrophic. It will drop the box. It will lose its balance and fall. It will collide with the obstacle. You cannot argue with gravity. You cannot debate the laws of physics. The physical world is the ultimate, non-negotiable fact-checker. This immediate, high-stakes feedback forces a level of robustness and grounding that purely digital AI can easily evade. The very act of putting an AI into a body subjects it to the unforgiving laws of nature, creating a learning environment that naturally selects for models that are better grounded, more cautious, and more aligned with reality. This is why many of the world's top AI researchers believe that embodied AI is not just a subfield of robotics, but perhaps the most viable, if not the only path toward the ultimate goal of the entire field: artificial general intelligence, or AGI. The theory is that a truly general intelligence cannot be developed in a digital vacuum. It must be forged in the crucible of the real world, through the continuous, closed-loop process of sensing, planning, acting, and learning from the consequences. The challenges are immense, but they are not roadblocks. They are the very frontiers of science and engineering that we must cross to build the next generation of intelligence. Join us next time on AI Deconstructed as we explore the ethical and societal implications of these rapidly advancing technologies. Until then, thank you for listening.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.